In relativity, the momentum of a material particle is denoted P, the vector P mu, it's equal to the mass times the velocity. So here's the world line of some material particle. World line is x mu parameterized by proper time tau. And the velocity of the particle is just the derivative of x mu with respect to tau. And the m that appears in this definition is often called the rest mass. But in relativity, mass and energy are equivalent, so this is also the rest energy. And what I mean when I say mass and energy are equivalent is that they're really the same thing. E equals mc squared, so they're just the same thing expressed typically in different units. So this factor c squared just converts the mass energy from units of kilograms into units of joules. Let's remind ourselves what this definition looks like in special relativity. In other words, we'll take the space-time to be flat with Minkowski coordinates. And we'll denote the Minkowski coordinates as t, and just using the non-relativistic notation x vector for x, y, and z. So in this case, the velocity has components partial t with respect to proper time tau and partial x vector with respect to tau. And this can be written as partial t with respect to tau times 1 comma partial x vector with respect to t. And you'll remember this factor is just the relativistic gamma factor. We've worked that out before. So this is just gamma times 1 comma v vector, where I'm letting v vector just be shorthand for dx dt. Now let's write down the momentum in special relativity. So that's just the mass times the velocity, so it's m gamma is the zero component, and the spatial components are m gamma v. The zero component of the momentum of the particle is the energy. This is the energy as opposed to the rest energy. Remember, m is the rest energy or rest mass. So m times gamma is the energy. The spatial components of the momentum vector are sometimes referred to as the relativistic momentum. As opposed to the non-relativistic momentum, which is just m times v. So the energy in particular is the zero component of the momentum, p0. How do we interpret this physically? Well, here's a picture of space-time. Here are the Minkowski coordinates. We have the t-axis, and then the spatial axes, x, y, z. And here's the particle moving along some world line. And what this energy is it's the energy of the particle as measured by an observer who's at rest in this Minkowski frame. So this is the energy of the particle as measured or seen by an observer at rest in these Minkowski coordinates, or the Minkowski frame. So in other words, this observer's world line is right along the t-axis. So this is the world line of the observer. And the velocity of the observer is, of course, just the vector 1, 0, 0, 0. So we can write the energy of the particle as measured by this observer in terms of the inner product between the observer's velocity, u, and the particle's momentum, p. Right? The expression is minus the inner product of u and p. So let's check this. We have minus the components of u, 1, 0, 0, 0, then the components of the metric, it's just the Minkowski metric, minus 1, 1, 1, 1 along the diagonals, and then the components of p, P2, P3. All right, so minus 1 times minus 1 is 1. So these first factors just give the vector 1, 0, 0, 0 times the P. So this is just equal to P0. So the energy is just the zero component of momentum. The advantage of writing the energy this way is that this is valid in any coordinate system, not just Minkowski coordinates. And by the principle of equivalence, this is the correct expression for the energy of a particle, even in the curved space-time of general relativity. Let me summarize what we've found so far. In general relativity, the momentum of a particle is the rest mass times the velocity of the particle. And we have an observer, and just so I don't confuse the velocity of the particle with the velocity of the observer, let me label the observer, say, give him a subscript A. So this observer has velocity U sub A. Right, the energy that the observer A sees for this particle is just the inner product of the observer's velocity with the momentum of the particle. Now, I'm going to get tired writing out inner products this way, so let's introduce a shorthand notation. So if we have two vectors v and w, let's just use the notation v dot w to stand for the inner product. So this would be shorthand for v mu, g mu nu, w nu. And using that shorthand notation, then the energy as measured by observer A for the particle is minus that's the inner product of the observer's velocity with the momentum of the particle. Now notice the rest mass m that appears in the definition of the momentum of the particle. This is really just the energy seen by an observer who's co-moving with the particle, so an observer for whom the particle is at rest. So m equals the energy measured by a co-moving observer. So if the observer is A, this is an observer whose velocity U sub A is equal to the velocity of the particle. So let's compute. The energy as seen by this co-moving observer is minus the inner product of UA with the momentum of the particle. But the momentum of the particle is just the mass times the velocity of the particle. So let's put the mass factor here. This is UA dot U. But if UA and U are equal, then this is just minus 1. So we find the energy as measured by this co-moving observer is just what we're calling the rest mass. So when we write down the momentum of a particle in terms of its rest mass and its velocity, we're expressing the momentum in terms of the energy that would be measured by a co-moving observer. But we can just as easily write down the momentum expressed in terms of the energy seen by some other observer. So let's consider a generic observer A. So this is any old observer, not a co-moving observer. So this observer measures the energy of the particle as minus UA dot P, but that's minus M times UA dot U. And we can now solve this equation for M. This is EA or minus EA divided by UA dot U. So replacing that in our definition here, we have momentum of the particle is equal to minus the energy as measured by some observer divided by the inner product between the observer's velocity and the velocity of the particle times the velocity of the particle. So now if we want to compute the energy as measured by some observer B, that would be E sub B equals minus the inner product of B's velocity with the momentum of the particle. So that's minus u sub B inner product with minus EA over UA dot U times U. And the inner product is between UB and U. The rest of this is just constant factors. So this is equal to EA divided by UA dot U times UB dot U. So we have the following result. The energy as measured by an observer B is related to the energy as measured by an observer A by the ratio of UB dot U with UA dot U times the energy as measured by A. So these results, and let's include this expression for the energy measured by B in terms of the momentum P. These three results define the momentum and energy of any particle moving along a time-like world line. And of course, if we specialize to the case where the observer A is co-moving with the particle, then the denominator here is just minus 1, and EA is just the rest mass m. So this is P equals m times U. And this expression, if UA is co-moving, the denominator here is minus 1, EA is m. So this is EB equals minus m times UB dot U. But the advantage of writing these expressions in terms of an arbitrary observer A, who is not necessarily co-moving with the particle, is that these same relations hold also in the case of a null particle, a light-like particle. The only difference between the time-like case and the light-like case is that in the light-like case we don't have the option of having our observer A co-moving with the particle. So let's shift our attention to the case of a light-like particle. Or a null particle, so a photon. And I'm going to write down the same formulas for energy and momentum, but I'm going to change notation a little bit. So instead of writing the fore velocity of the particle as u, which of course that's the same thing as partial x mu with respect to proper time tau, since we don't parameterize a null world line by proper time, we'll just use the notation x dot mu instead of u. So the dot here will refer to differentiation with respect to some affine parameter lambda. So this is x mu dot, a function of lambda. And also recall that the energy for a photon is equal to Planck's constant times the frequency. So h is Planck's constant. And f is the frequency. And we'll set h equal to 1. So E is just the frequency f. So I'll replace energy with frequency. With these changes in notation, we can write these results for the momentum and energy of the particle as follows. So the momentum of the photon is equal to minus the frequency as measured by some observer, call that observer A, divided by the inner product between A's fore velocity and the tangent to the photon world line times the tangent vector. And we have the frequency measured by any observer B is minus the fore velocity of B inner product with the momentum of the photon. And if we combine these two equations, we find the frequency measured by B is equal to UB dot the tangent x dot divided by UA dot the tangent x dot times the frequency measured by A. Let's look at an example. So let's take flat two-dimensional space-time with Minkowski coordinates. So the metric is just minus 1001. And now for the photon world line, let's take the tangent to be 1, 1. So here's our Minkowski diagram, and here's the world line of the photon. Now you'll notice that the tangent vector is normalized, so the inner product of x dot with itself is 0, and that inner product uses this metric. I could have just as easily written 2, 2 or 3, 3 for the tangent vector. And what that means is, if this is the scale on the Minkowski diagram, by choosing 1, 1, if I think of that as a displacement vector, this is the vector that I've just drawn here. So it has length 1 in the x direction and length 1 in the t direction. But I could also take the tangent vector to be 2, 2, so I could take it to have length like this. Okay, these are both tangent vectors to this world line. So these are both tangent vectors to the world line, 1, 1 and 2, 2. And they're both normalized to 0, normalized in the proper sense using the metric. The sense in which this vector is longer than this one is just that its projection to the x or t axes is longer. So it looks longer in this diagram, but both of these have proper length 0. And in the end, it's not going to matter whether we choose, for example, 1, 1 or 2, 2, because notice the physical quantities here, the momentum and the frequency, they depend on x dot with a factor in both the numerator and denominator, here and here. So if I rescale x dot, say by a factor of 2, it doesn't matter. That factor of 2 cancels in these expressions. So now let's choose our observer A to have 4 velocity gamma A, comma, gamma A, VA. So here gamma is just a familiar special relativistic gamma factor, 1 over the square root of 1 minus VA squared. And we'll take our observer B to have 4 velocity gamma B, comma, gamma B, VB. And you can of course check that these are both normalized. So UA dot UA is minus 1, UB dot UB is minus 1. Let me redraw the picture. Here's the Minkowski diagram with the photon and our observers. Here's the observer A with 4 velocity UA. Here's our observer B with 4 velocity UB. And now the frequency as measured by B is related to the frequency as measured by A. Let me write it as a ratio. This is equal to UB dot x dot divided by UA dot x dot. So let's first compute UB dot x dot. Okay, UB is gamma B, comma, gamma B, VB, and the dot is the metric, minus 1001, and x dot, remember, is 1, 1. Okay, so multiplying these two factors together first, we have gamma B times gamma B, VB, then this is minus 1, 1. So we have minus gamma B plus gamma B times VB. And we can simplify that a bit, pull out the factor of minus gamma B times 1 minus VB. And gamma B, remember, is 1 over the square root of 1 minus VB squared. But we can write 1 minus VB squared as 1 minus VB times 1 plus VB. And then this result simplifies to minus square root of 1 minus VB divided by 1 plus VB. And of course we have a similar expression for UA dot X dot. So the ratio of frequencies here, FB over FA, is equal to, the minuses cancel, so we have square root of 1 minus VB over 1 plus VB times the square root of 1 plus VA divided by 1 minus VA. So this is the general result for the relationship between the frequencies measured by two different observers. And we can write this in a little bit more familiar way by let's let the observer A have velocity equal to 0. And what that means is the observer A is at rest in the Minkowski frame. So in our picture, the observer A is just moving right along the t-axis. All right, in that case, with VA equal to 0, we have FB over FA is equal to square root of 1 minus VB over 1 plus VB. And now this is, or should be familiar, as the special relativistic Doppler shift. Let's carry out a quick check. So here's the Minkowski frame. Here's the photon. And let's say our observer B is moving along with some positive velocity, so VB is greater than 0. And of course the observer A is moving right along the t-axis. So if VB is positive, that means 1 minus VB divided by 1 plus VB is smaller than 1. So in this case, we have FB is less than FA, right? And that makes sense because the observer B is moving along with the photon in the same direction as the photon. So that observer would measure a lower frequency than the observer A. And of course, if we look at it the other way around, here's the case where VB is negative. So this is VB positive. If VB is negative, then we find this factor is greater than 1. So the frequency is greater for B is greater than the frequency for A if VB is less than 0. And in that case, observer B is moving towards the photon and sees it at a higher frequency. Let's return now to the general case of curved spacetimes, and I want to summarize some of the things we found. So this is the world line of a material particle with 4 velocity u, and what we know is that the energy of that particle is measured by some observer B is related to the energy measured by an observer A by the ratio of UB dot U to UA dot U. So, for example, here's the observer A with 4 velocity U sub A. Here's my observer B with 4 velocity UB. And we also have a photon. So let's say here's a photon with tangent vector x dot. And now the frequency measured by observer B is related to the frequency measured by observer A by the ratio of UB dot x dot to UA dot x dot. One thing that's important to notice about these formulas, and it's really hidden in the notation, is that these inner products are to be evaluated locally where the observer crosses the world line of the particle or photon. So for example, this UB dot U, this observer B is going to measure the energy of this particle, and the observer measures the energy at this event or locally near this event. And likewise, UA dot U is measured locally near this event. UB dot x dot is here at this event, and UA dot x dot is at this event. All right, so when we evaluate these mathematically, we have to make sure that we compute these inner products correctly, taking into account where they are being evaluated. It's time for an example. Let's apply this result to the Schwarzschild spacetime. So we will apply the result, which says that the frequency of a photon measured by some observer is proportional to the inner product between the observer's Fourier velocity and the tangent vector to the photon geodesic. So we have this result, and we'll apply that to Schwarzschild. So I've written out the geodesic equations here for Schwarzschild. Let me remind you that in Schwarzschild coordinates, the metric is minus 1 minus 2m over r dt squared plus 1 minus 2m over r inverse dr squared plus r squared times d theta squared plus sine squared theta d phi squared. Because we're considering a null geodesic, the norm of the tangent vector is 0. And furthermore, let's consider the photon to move along a radial direction. So we want to find a radial null geodesic. And by radial, I mean a geodesic that moves along some theta equal constant, phi equal constant world line. Now you might ask, how do we know that the geodesic equations have any solutions with theta and phi equal to a constant? Well, I think it's intuitively obvious that photons can travel along radial directions, but the argument would be, by symmetry, if we start a photon moving in the radial direction, there's nothing in the space-time that would cause it to curve. Or said another way, if it were to curve in one direction, why doesn't it curve in another direction? So there needs to be some sort of asymmetry in the space-time to cause the photon to deviate away from that radial direction. So let's look at these equations, the geodesic equations, with theta and phi both equal to constants. So this equation is just 0 equals 0, and likewise this equation just says 0 equals 0. This term goes away, this term goes away, and in the normalization expression, these two terms go away. So we have these two second-order equations, and we have already a first integral of those equations here, and of course we have another first integral because of the killing vector field d by dt. So remember, d by dt is a killing vector field, and it's obviously a killing vector field because the metric components are independent of t. So let's apply a result that says that the inner product between the killing vector field and the tangent to the geodesic is a constant. So we have k dot x dot is equal to constant. And if we work that out, k has components 1, 0, 0, 0. We have then the components of the metric, and then the components of the tangent vector, which are just t dot, r dot, and since we're assuming theta and phi are constant, then these are zeros. So we, of course, worked this out in a previous lecture when we were analyzing orbital motion in Schwarzschild. This is just minus 1 minus 2m over r times t dot, and that's equal to a constant which we can let it equal minus e, just like we did in the orbital case. So we now have another first integral of the equations of motion that says t dot is equal to e over 1 minus 2m over r. So this result, along with the normalization condition, constitute two first integrals of these two geodesic equations. So let's now write down this result explicitly. If we bring this term to the right-hand side and divide through by 1 minus 2m over r and take the square root, we're just left with t dot equals either plus or minus, because we've taken a square root, r dot divided by 1 minus 2m over r. These equations aren't too difficult to solve, and I'll do that in a moment, but first let me point out that if the photon is above the surface of the Earth or outside the surface of the Sun, then 2m over r is very small, which means the denominator here and here is always positive. Now, also remember that the dot denotes d by d lambda, so it's differentiation with respect to the affine parameter lambda. And if we assume that the t coordinate increases with increasing lambda, then t dot is positive. So that tells us that e, the constant e here, is going to be positive. Now in this equation, since t dot is positive and the denominator is positive, the plus sign just corresponds to r dot being positive, which means the photon is moving radially outward. Whereas the minus sign corresponds to r dot negative, and that's the photon moving radially inward. So just to be concrete, let's assume that we're dealing with the case in which the photon is moving radially outward. So we'll take the plus sign in this equation. So with this choice, we can see from these equations that r dot is equal to little e, and then t dot is little e divided by 1 minus 2m over r. Now the r dot equation has solution r of lambda equals e lambda plus r naught. So this is a constant of integration, which is the value of the areal radius when the parameter lambda is equal to 0. And now this second equation can be written as dt equals e divided by 1 minus 2m over r, but r is e lambda plus r naught times d lambda. And we can integrate this equation to find t as a function of lambda. The result is t of lambda equals e times lambda plus 2m times log of 2m minus e lambda minus r naught, plus, of course, an integration constant. And the integration constant just determines the value of t when lambda is equal to 0. And really, we can pick that to be any t value we like, because remember that Schwarzschild spacetime is static, which means that each t equal constant slice is equivalent to every other t equal constant slice. So we might as well choose t of 0 to be 0. And in that case, then t of lambda is e lambda plus 2m times log of 2m minus r naught minus e lambda divided by 2m minus r naught. So here's our solution explicitly for the null geodesics moving along the radial directions in Schwarzschild spacetime. Now let's compute the ratio of frequencies of this photon as seen by two different observers. Before I do that, let me remark about the constant E. You might be wondering what its value is. Well, the answer is it doesn't matter. You notice little e just multiplies r dot and t dot, so it's just a multiplicative factor for the tangent vector to the null world line. And as we saw in the case of special relativity, the length of the tangent vector doesn't matter. And by length, I mean the projection along the x or t axes. So nothing physical is going to depend on this parameter little e. And in fact, notice in these equations we could absorb little e into the affine parameter lambda. So little e is just a constant. We could use it to just rescale lambda everywhere lambda appears. So e doesn't matter. And by that I mean its value doesn't matter as long as it's not 0. But just to emphasize the point, I'll go ahead and leave little e in the calculations. So the plan is to compute the ratio of frequencies of the photon as measured by two observers A and B by computing the inner product between UA and UB with the tangent to the null world line. So we need to choose observers A and B. Let's choose both A and B to be stationary observers. In other words, they'll sit at a constant r theta phi location. So for observer A, will be at an areal radius a sub a, and theta equal constant, phi equal constants. And for observer B, areal radius r sub b with theta equals the same constant and phi equals the same constant. So here's the picture. We have our spherical body of mass m, and here's areal radius a. So our observer A sits at this areal radius. Here's areal radius B. And we have a photon that's moving radially outward, passing the observer A and the observer B, and we'll compute the inner product between A's world line for velocity and the tangent to the null ray at this point, and we'll evaluate UB dot x dot at this point. And their ratio then gives us the ratio of the frequencies. So let's start by writing down the world line for observer A. So observer A has the world line given by x mu of tau equals tau divided by the square root of 1 minus 2m over r sub a, comma, r sub a, comma, 0, comma, 0. And we can check that the for velocity for A, that's just x mu, and this is for observer A. I'll put a little subscript a there. That's just the tau derivative of x mu of A. That's equal to 1 over the square root of 1 minus 2m over r sub A, comma, 0, comma, 0, comma, 0. And we can check that UA dot UA is properly normalized to minus 1. And now for the photon, I'll remind you that the photon world line is given by x mu of lambda, which is equal to E lambda plus 2m times log of 2m minus r naught minus E lambda divided by 2m minus r naught. That's the first component, the 0 component. The second component is just E lambda plus r naught, and the final components are just 0. So we need to first figure out where these two world lines cross. All right, that's not too difficult to do. We can equate the 1 components, the r components. So r sub a is equal to E lambda plus r naught, or E lambda is equal to big R sub a minus r naught. And then we can plug that result into the 0 components and equate them. So we have, from here we have RA minus R naught plus 2m times the natural log of 2m minus R naught, but that will cancel the minus R naught from E lambda. So we just have 2m minus R sub a, all of that divided by 2m minus R naught. And that's the 0 component of the photon world line. The 0 component of observer A's world line is tau over the square root of 1 minus 2m over R sub a. And now we can solve these two equations for lambda and tau explicitly in terms of the parameters of the problem, and then substitute those results into these world lines to get the coordinates of the event where they cross. And the details aren't really important in this simple case. The only thing that matters is where they cross is at areal radius r sub a. Now we need to write down the tangent vector to the photon world line. That's just x mu dot. So it's obtained by differentiating this with respect to lambda. And the components we've computed before, t dot, r dot, and of course theta dot and phi dot are 0. So t dot was just E divided by 1 minus 2m over r. And now this is r of lambda, which is r of lambda is E lambda plus r naught. And this component, r dot, is just E. So this is the tangent vector to the photon world line. And now we're finally ready to compute the inner product between UA and X dot. So we have UA inner product with X dot. UA, you'll recall, is 1 divided by the square root of 1 minus 2m over r sub a, then comma 0, 0, 0. The metric is minus 1 minus 2m over r is the 0, 0 component. The 1, 1 component is 1 minus 2m over r inverse. And then we have the other components, and all of the off-diagonal terms are 0. And then X dot has 0 component e divided by 1 minus 2m over r of lambda, and e 0, 0. And all of this is evaluated where the photon and the observer A cross, in other words, at areal radius r sub a. So all of these little r's, here, here, and here, are equal to r sub a. So simplifying this, multiplying the first two factors together, we have minus square root of 1 minus 2m over r sub a, comma 0, 0, 0, times this vector, e over 1 minus 2m over r sub a, e 0, 0. And then that equals minus little e divided by the square root of 1 minus 2m over r sub a. So that's equal to UA dot X dot. Of course, we can repeat the same calculation for observer B, and we'll find the corresponding result UB dot X dot is equal to minus little e times the square root of 1 minus 2m over r sub b. So our result for the ratio of frequencies, FB divided by FA, is UB dot X dot divided by UA dot X dot. So that's square root of 1 minus 2m over r sub a divided by the square root of 1 minus 2m over r sub b. Notice the constant little e drops out from the final result as expected. So now let's take a look at this result. We have, let me draw a picture first, the same picture we had before. Here's the central body of mass m. Here's areal radius A. Here's areal radius B. We have our observers sitting at those radii, and there's a photon moving radially outward. So this is the photon. And now, because RB is greater than RA, that means, relatively speaking, RB is large, 2m over RB is small, 1 minus something small is large. So the denominator here is larger than the numerator, which tells us that FB over FA is less than 1, or FB is less than FA. So the frequency as measured by observer B is smaller than the frequency observed by observer A. So A might see this photon as a blue photon with relatively high frequency, but B would see the same photon at a lower frequency, say as a red photon. So this effect is referred to as the gravitational redshift. So in speaking in Newtonian language, we think of the photon as losing energy as it climbs out of the gravitational field. So as it loses energy, it shifts in frequency from blue to red. So this is the result for the gravitational frequency shift for a photon moving radially in the Schwarzschild geometry. But what about non-radial photons? So we have our central body of mass m. Here's the areal radius r sub a. And here's the areal radius r sub b. And the photon could follow a path, say like this. All right, what's the frequency shift in this case? Well, it turns out exactly the same result holds. And there's a simple trick to show that. If you recall, the forward velocity for observer A has components 1 over the square root of 1 minus 2m over r sub A, comma 0, 0, 0. So this is proportional to the vector 1, 0, 0, 0. But this vector, these are the components of a killing vector field, k. So we can write the forward velocity for observer A as this constant, 1 over the square root of 1 minus 2m over r sub A, times the killing vector field k. And likewise for observer B, we have u sub B is equal to 1 divided by the square root of 1 minus 2m over r sub B times the killing vector field k. So now when we compute the ratio of frequencies, f sub b divided by f sub a, that's ub dot x dot divided by ua dot x dot, where x dot is the tangent to the null geodesic. And now that null geodesic doesn't have to be radial. It can be in any null geodesic. So u sub b is, we have, in the numerator we have k dot x dot divided by the square root of 1 minus 2m over r sub b. And for the denominator we have k dot x dot divided by the square root of 1 minus 2m over r sub a. And now remember, anytime we have a killing vector field and a geodesic, their dot product, their inner product, is a constant. So even though we're evaluating these dot products at different points in the space-time, they're constants because they're constants along the geodesics. So these two factors cancel, and we're left with the result that we had before for radial geodesics, namely 1 minus 2m over r sub b divided by square root of 1 minus 2m over r sub a. So this is fb over fa, and it's a general result that holds for any null geodesic. So this result shows the gravitational redshift for any photon in the Schwarzschild geometry. This result actually has some important implications. Let me draw the picture once again. Here's areal radius r sub a, areal radius r sub b, and here's the light traveling past A and past B. And let's say that observer A measures the frequency of that light, f sub a, as 1 times 10 to the 14th hertz. So observer B would see the frequency of the light as being redshifted to maybe 1/2 times 10 to the 14th hertz. So in other words, observer A, looking at the electric field in this light wave, would see successive wave crests occurring with a period of the inverse of this, 10 to the minus 14 seconds between peaks of the electric field. Observer B would see a time period between peaks of the electric field as twice this. So the inverse of 1/2 times 10 to the 14th is 2 times 10 to the minus 14th seconds. And now let's string this picture out to a bunch of wave crests. So here's RA, here's RB, and we have a bunch of peaks in the electric field. Let's look at 10 to the 14th oscillations of the electric field, or 10 to the 14 wave crests. Right? That means that for observer A, between these events, the time period that has elapsed is 1 second. Whereas for observer B, the time between these events is 2 seconds. Now let's scale this picture up even further. Let's say for observer A, let's look at the two events where the elapsed time is, say, 10 years. For observer B, the corresponding events, there would be a time elapsed of 20 years. So for A, the time between these events is 10 years, and that's time as measured on any clock, any mechanical clock, or sand flowing through an hourglass, or any biological clock as well. So observer A actually ages by 10 years from here to here, and A can prove that to their friend B by sending pictures of himself. From this event, A takes a picture and sends it off. Again, A takes a picture here and sends it off to observer B. Observer B looks at those pictures and says, yes, it certainly looks like you've only aged 10 years, but it's taken you 20 years to do so. I've aged by 20 years during that same time that you've only aged 10 years. Observer B says, your clock is running slow. But of course, A says the opposite. A looks at the pictures of B. In only 10 years, B is aged by 20 years. So A would say, your clock is running fast. And these results are sometimes summarized by the statement, time runs slow deep in a gravitational field. Now this physical effect is very real, and it's very important to take into account. For example, in the global positioning system, the GPS satellites orbit at a radius of about 2.7 times 10 to the 7th meters, and the radius of Earth is about 6.4 times 10 to the 6th meters. And there are clocks in the GPS satellites and clocks on Earth that are constantly communicating with one another and have to stay synchronized. Now, of course, the satellites aren't stationary. They're changing their angular position as they move through the Schwarzschild geometry. But let's ignore that fact for the purpose of this quick calculation. We know the ratio of frequencies is square root of 1 minus 2m over r sub a divided by the square root of 1 minus 2m over r sub b. And if we put in the radius of the orbit of the GPS satellites, the radius of Earth, and the mass of the Earth for m, let's remember this is actually 2gm over c squared times r sub b. If we put these numbers in, we find the following result. This is approximately 1 minus 5 times 10 to the minus 10. So this is the fractional change in frequency, and it's also the fractional change in the rate at which the clocks run. So for every 1 second that passes on Earth, the clocks on the GPS satellites experience a change of 1 plus 5 times 10 to the minus 10 seconds. And this is a big enough difference to affect the accuracy of the GPS system. In fact, the clocks on the GPS satellites are constantly being recalibrated to stay in synchronization with the earthbound clocks. And without that constant synchronization, the GPS system would become relatively useless within a matter of minutes.